Okay, we'll get back to section 6.4. We're talking about work applications, and so we looked at an example where we had a variable force, and more times than not, any like physics-related problem is going to be where there's going to be a variable force going on. Okay, I mean sometimes it's a constant force, but when we have a variable force, we need to use calculus in order to calculate the work done to complete a task. So let's see, we did problem 4. One application that might be easy to visualize for a variable force and how it relates to the amount of work is the stretching and compression of a spring. Here's a definition. According to Hooke's law, which is a law in physics, the force F required to compress or stretch a spring within its elastic limits is proportional to the distance x that the spring is compressed or stretched from its original length. That is, F equals k times x, where the constant of proportionality, k value, is sometimes called the spring constant, depends on the specific nature of the spring. Okay, let's take a look at problem 5. A force of 750 pounds compresses a spring 3 inches from its natural length of 15 inches. Find the work done in compressing the spring an additional 3 inches. Okay, so of course this would be a variable force, since when you compress a spring, the force required to compress a spring is going to change throughout the time period as the spring is being compressed. Now we're going to want to find the k value here in this problem and then set up an integral. Okay, we're going to be integrating a force function, and we've got to find f of x. Like I said, I got to find this k value here. Now we're told that a force of 750 pounds compresses a spring 3 inches from its natural length. Okay. X is the length that you're compressing the spring in this case. Okay, so if I let x be 3, f be 750 divided by 3, k would be 250. Okay, and that would be the spring constant for this problem. So if x is 3, you compress the spring 3 inches. 750 pounds would be required. Okay, if you compress it x inches, 250 times x pounds would be required. Okay, so I'm going to want f of x going inside my integral. Now I want to find the work done in compressing the spring an additional 3 inches. Okay, so I'm already at 3 inches into it. I'm going to start at 3 and go an additional 3 inches. So I want the bounds in my integral to be 3 to 6. Okay, antiderivative would be 250x squared divided by 2, or 125x squared. We're evaluating that from 3 to 6. Plug in the bounds, and I'm getting 3,375 inch-pounds. If you wanted to convert that to foot-pounds, which wouldn't be a necessary thing, but if you wanted to do that, divide this number by 12, and you'd get 281.25 foot-pounds then would be that value. Now, notice that in this problem we do not integrate from 0 to 6, since we are asked to determine the work done in compressing the spring an additional 3 inches. Okay, we're not including the first 3 inches in setting this up here. Now, should the work done in compressing the spring from 0 to 3 inches be more than, the same as, or less than 3,375 inch-pounds? Well, it's going to be less, right? Because, in fact, if you were to calculate W, you'd get 1,125 inch-pounds. If I were going from 0 to 3, that's what I'm getting there. And of course, that number would be less because in order to compress it further, there's going to be more force applied, right? So more work would have to be done. Okay, problem 6. A force of 250 newtons stretches a spring 30 centimeters. How much work is done in stretching the spring from 20 centimeters to 50 centimeters. Okay, well, I'm in the SI metric system, right? So I got to make sure that my answer here when I compute W is going to be in Newton meters, or joules is the same thing. I got to find the spring constant. Now this formula applies for compressing or stretching a spring. Okay, so it's going to be very similar to what we just did there in problem 5. I got to find K. The force is 250 newtons to stretch a spring 30 centimeters. X would be the length that the spring is stretched. Okay, 250 would be F, and if you divide then and reduce, K is 25 thirds. So F of X is 25 thirds X. That's going to go in my integral. How much work is done in stretching the spring from 20 centimeters to 50 centimeters? Well, I'd set up my bounds there and then integrate. When I plug in the bounds, I'm getting 8,750 Newton centimeters, which if you divide by 100, you'd get the result in Newton meters. 87.5 Newton meters, or 87.5 joules, would be the answer. Okay, now pay attention to the units that are given in the problem. Okay, so if they're describing something as like centimeters, don't blindly write meters. Okay, or if something is described in inches, don't blindly write feet. Okay, and there's problems in the book where the units are different. Okay. Let's take a look at problem 7. If the work required to stretch a spring 1 foot beyond its natural length is 12 foot-pounds, how much work is needed to stretch it 9 inches beyond its natural length? Okay, well, it's going to be less than 12 foot-pounds, right? Since you're not stretching it as far, there's going to be less work required. Now, 12 foot-pounds is the work required to stretch the spring 1 foot beyond its natural length. So I know I'm going to be integrating a force function, f of x equal k times x. And my bounds here, I'll go 0 to 1, since I'm stretching the spring 1 foot to get 12 foot-pounds then. Now when I integrate, k is a constant, I'm going to have k times x squared divided by 2. When I plug in the bounds, I'll get 1/2 k. 12 equal 1/2 k means that k is 24. Okay, so now I want to find the work done in stretching the spring 9 inches beyond its natural length. K is 24, so inside the integral, the integrand would be 24x. And my bounds, I'm going to go 0 to 3/4. Now, again, pay attention to the units here. We're going 9 inches. Here's 1 foot. 9 inches is 3/4 of a foot. Okay, I'll have students mess this up and they'll go 0 to 9. They're not paying attention to the units there. So we've got the bounds set. Integrate and plug in the bounds, and I'm getting 6.75 foot-pounds. Of course, that sounds reasonable since that number is less than 12. We're not stretching it as far. In fact, that is correct. Okay, but that'd be how that problem goes there. We'll go to the next page. Another interesting work problem is when we apply gravitational force to a moving object. The gravitational force exerted on an object with a mass m is where you take mass times acceleration due to gravity, 9.8 meters per square second on Earth. When an object such as water, a rope, or a chain is lifted, then different amounts of work are required since different parts of the object are lifted different distances. Because there would be a variable force, then integration is necessary if you're lifting objects. So let's take a look at the kind of the last couple of problems here are going to be where you're lifting objects with a variable force. Okay. Problem 8, a 1,600 pound elevator is suspended by a 200-foot cable that weighs 10 pounds per foot. How much work is required to raise the elevator from the basement to the 3rd floor, which is a distance of 30 feet? Okay. Well, this is a variable force with the cable. Now, the weight of the elevator is 1,600 pounds. That's not changing in the problem. Okay, so there's going to be two parts to this. One part is where I want to find the work done to lift the elevator, and then also the work done to lift the cable. Okay, again, the elevator is, the weight of the elevator is not changing in the problem, so I have a constant force there, and I would just take the weight times the distance. So 48,000 foot-pounds would be just the work done to lift the elevator. Okay, now how about lifting the cable? Well, the cable is a variable force. Since different sections of cable are going to be lifted, the weight is going to change throughout the problem. All right, now when I set up my integral, I'm going to be integrating a force function where the units are going to be in pounds. Okay, now we're lifting the elevator from the basement to the third floor, which is a distance of 30 feet. My bounds on the integral are going to be 0 to 30 then. The cable weighs 10 pounds per foot. Now, I'm going to let y represent the distance that the elevator is going to be lifted to, and then since the cable is 200 feet long, 200 minus y would be the length of the cable still hanging. Okay, now you have 10 pounds per foot times the length of the cable that's still hanging there is 200 minus y feet. Okay, feet are going to cancel there, going to leave me with an expression involving pounds inside the integral. A pound is the U.S. customary unit for force. So if I were to let y be 0 here, I would have 200 feet of cable hanging. Okay, if y is 30, then I would have 200 minus 30 is 170 feet of cable is still hanging. So you would have lifted the elevator then 30 feet in order for 170 feet to still be hanging there. So here'd be my setup integral, and can distribute the 10 and integrate. When you plug in the bounds, so I was getting 55,500 foot-pounds. Okay, W then would be the total weight, that is to lift the elevator and the cable. By adding that, I'm getting 103,500 foot-pounds then is the answer. Problem 9 is a similar problem, so let's take a look at that one next. A chain is laying on the ground, and it is 10 meters long, and its mass is 80 kilograms. Okay, so I'm in the SI metric system here with that information given. How much work is required to raise one end of the chain to a height of, that should be 1 by the way, one end of the chain to a height of 6 meters? Well, you can think about this problem as how much work is required to raise one end of a 6-meter chain to a height of 6 meters. Since the other 4 meters are still on the ground, and it doesn't have a force acting on it. Okay, so that's how I'd like us to think about the problem. Just, you know, we've got a 6-meter long chain. We're going to lift it so that it's fully extended. Well, the chain, if it is initially 10 meters long and its mass is 80 kilograms, then 8 kilograms per meter is what we're looking at. Now, I want to find the weight density of the chain. Just like in this last problem, I had to find the weight density of the cable. Okay, that's what I'm doing here to figure out this force function. and I'm going to do a similar thing here. Okay. Now, in this problem, since I've got the working in the SI metric system, I'm going to have to figure in the acceleration due to gravity. Okay, and that is 9.8 meters per square second on Earth. They told us there that information up here. Okay, so by multiplying these two numbers, 1 kilogram times 1 meter divided by 1 square second, that is by definition 1 Newton. I've still got an extra meters down under, okay, there. So newtons per meter would be my unit measure that I'd give at the end when I multiply these two numbers together. Now, inside the integral, I need newtons. Okay, so I'm going to be multiplying this result here by something that is in terms of meters. Well, suppose that we lift the rope, or the chain in this case, up to a height of y meters above the ground. Then 6 minus y meters would be left. Okay, the bounds here, I'm going to go 0 to 6, since I'm thinking of this as a 6 meter chain, and then we're going to lift it so that it's fully extended. Okay, if we take 78.4 newtons per meter times 6 minus y meters, meters cancels, and that leaves us with something in terms of newtons, which is the unit measure for force if you're in the SI metric system. Now, if y is 0, then all 6 meters would be on the ground. If y is 6, 6 minus 6 is 0, so you have 0 meters lying on the ground, and it would be fully extended then in that case. There's my setup, so I would integrate, plug in my bounds, and I get 1,411.2 joules then is the answer. Okay, and of course these two problems are very similar, but it's all about a variable force, right? As the chain is being lifted, more links are being added to what's already there, and so the force is going to vary throughout the calculation, which means that the only way to do this problem is by using calculus, right? We need an integral setup. There's just the last lifting type problem that I was going to show you is coming up here. We're going to be lifting water from a tank, and so I'll talk about that in the next video and kind of wrap up the chapter then.